see my screen?
Yes, please.
Yes, please.
Yes.
All right, perfect. So this week we're going to start talking a bit about probability, but we're also going to keep using a lot of the techniques that we learned in the previous 3 lectures about counting to actually calculate those probabilities. But just to get started, we'll talk about basic probabilities and then we'll get into more complicated questions and techniques. And in today's lecture, I'm going to do a mix. Well, I'm going to try to do like a lot of different practice problems, so you can see a mix of different types of probability questions. Just to start off with, is everyone familiar with what probability is? Have you seen this in school or in kind of other math books that you've read?
Yeah.
Yeah, okay. Awesome. Well, then I'll just go over it really quickly, but feel free to stop me if you have any questions. So basically, probability is the probability of an event is sort of like figuring out what is the percentage of time that this event might happen. And so we can use an example to illustrate. So say we have 6 marbles in a bag, and the marbles we have 1 blue marble, 2 red marbles, and 3 green marbles. And then say the marbles are the same size, shape, and weight. So when you're reaching into a bag and trying to grab it, you have an equal chance of grabbing any of the marbles. Then if we can count sort of equally likely outcomes of the event, then we can determine the probability of some event by counting the number of total successful outcomes over the number of total outcomes. So for example, if we have 6 marbles and we want the probability of selecting 1 blue marble, and we have 1 blue marble, 2 red marbles, and 3 green marbles, then we can compute the probability of selecting the blue marble here. And then the number of successful outcomes is 1, which is just there's 1 way to select the blue marble over 6 because there's 6 total marbles. And so the probability of selecting the blue marble is 1/6. So this is a very simple example, but I just want to make sure everyone understands the concept because we'll build on top of it. Does anyone have any questions before we move on?
Please.
All right. So this is just a, as I mentioned, pretty simple example, and probability problems can get much harder than this one. But basically using this concept of the probability of event equals the total number of successful outcomes over the total number of outcomes. Whenever you have sort of some countable number of equally likely outcomes, will help you solve one class of probability problems. And in future weeks, we'll talk more about other types of problems, but we'll start with this type for probability using counting. Just as a preview, in future weeks, we'll talk about kind of algebra and geometry as ways we could use those techniques to calculate probability. So I think the best way to really grasp this concept is to do a bunch of examples. This handout, which I shared in Piazza, has much more examples plus solutions to them, but we'll go through some of them in class together. So I picked a few. So let's start with this one. So this one says a card is randomly selected from an ordinary deck of 52 playing cards. What's the probability that it is a red face card? And a face card means it's a jack, queen, or king. Any volunteers on how to solve this one?
Yeah. Since there are two red playing cards like diamond and the love, so it will be 2 times 3, which is 6 over 52, and can reduce it to 3 over 26.
Yeah, awesome. So let's go remember the formula. So probability of a red face card. We can say how many red face cards there are over total number of cards. So we know there's 6 red face cards because there's 2 suits, and then for each suit there's 1, 2, 3 cards. Oh, sorry. And then there's 52 cards total. So this gives us 3 over 26. Any questions? Alright.
Yeah, how
No,
do you know that there are two?
Sorry?
How do you know that there are two before you multiply it by the 3?
Oh, okay. So a deck of playing cards has 4 suits. So basically there's, if you're familiar with playing cards, there's like hearts, diamonds, and then in black there's like clubs, which kind of looks like this, and spades. I can't draw spades. So then, and then for each suit, there's 13 different cards. So there's ace, and then 2, 3, 4, all the way to 10. And then there's jack, queen, king. So that's what makes up a deck of cards. So then if we want to count the number of red face cards, we know there's 3 face cards per suit, and then there's 2 red suits. All right, let's try a different one. This is more about rolling dice. And similar concept here, because rolling, if you roll a fair or ordinary 6-sided dice, you have an equally likely chance of landing on any face. So let's try the first one. Find the probability that the result is 4. Any volunteers for this one?
1/6.
Yep. So this is just 1/6. Again, if we use the formula, it's number of successful outcomes over number of total outcomes. So there's 6 total outcomes, and only one of those is a 4. What about problem? Oops. What about problem B? So find the probability that the
Half.
result is even.
I think that'll be half.
Yep. So number of total outcomes is 6. But then the number of even outcomes, there's 3 of them, because you could roll 2, 4, or 6. So you get 3/6, which is 1/2. That's right. All right, and then what about problem C? Find the probability that the result is greater than 2.
2/3.
So greater than 2, there's 4 possibilities, 3, 4, 5, 6. So you get 4/6, and that gives you 2/3. Are you guys finding this? You understand this? Pretty easy? Or any questions? All right, I'll take that to be no questions, and we'll move on to just slightly harder problems. All right, so this one's a bit more complicated. Here we're saying we're rolling 2 fair standard 6-face dice. What's the probability of rolling the same number on both dice?
Would that be 6/6 factorial or 6/36? I'm not sure about the total outcome.
Yeah, that's close. So again, we want to count probability same on both equals number of outcomes where we have 2 same numbers on dice, and then over number of total outcomes. And in this case, for the number of outcomes where it's two of the same numbers on dice, there's 6 because you can have 1, 1, 2, 2, 3, 3, 4, 4, and 5, 5, right? For the total, you mentioned a couple. You said 6 factorial or 6 times 6. So in this case, anyone else have any ideas on which one it could be?
This could be 6 choose 2.
It could be 6 choose 2. That's another possibility. So I'll write
But
down
most
some
of them be
things.
also 6 and 6. Rolling 6 on both sides.
Give me the calculator.
I think it's 2 to the power.
So some people shouted out 6 factorial, 6 times 6, 6 choose 2. What do you guys think it is?
I think it's
6.
6 out of 6 raised to the power 6.
Sorry? Say
I
that
think it's
again?
Yeah.
36.
6 out of 6 raised to the power 6.
All right, some people said 6 to the power of 6. Did I miss
I think-
any others?
I think
Yeah.
it's
No,
36.
6
out
is the
of
power
6
2.
raised to the power 6.
3 to the power of 6?
No, 6 is the power 2.
2 to the power of 6?
Or the opposite. 6 is the
Divided
power
by
2.
I think
6
it's 2
raised
to
to
the
the
power
power
6.
6.
Do you mean 6 to the power of 2?
Yes.
Okay, yeah, so that's this one. Yeah, so these are all different sort of guesses. So the answer is actually 6 squared. There's a couple ways you can think about this. So the first one is you can kind of try to reason about it just by like writing out all the different possibilities. So if you have, use a different color. If you have 2 dice, let's call it die A and die B, then you could roll, 1 for A, 1 for B, 1 for A, 2 for B, 1 for A, 3 for B, 4, 5, 6, and then same for 2. And basically what you'll see is for every value of A, there's 6 values of B. And so you would get 6 times 6. Another way is you can just think about, like, it's kind of the same reasoning, but without writing it out, you can think, okay, for the first dice, or the first die, I have 6 possibilities. For the second die, I also have 6 possibilities, and I can combine them in any of those combinations. So I multiply, I get 36. Some of these other ones, 6 factorial doesn't quite make sense because that is sort of saying how many ways can I permute 6 different numbers. 6 choose 2 is close. So 6 choose 2 would be if I wanted to pick, say, like 2 numbers out of 1, 2, 3, 4, 5, 6, and the order doesn't matter, and I don't replace it. So if I had to pick 2 numbers and they had to be different and they were subsets, then there would be 6 choose 2 subsets. So they're all, these are like counting different things. So in this case, we recognize the thing we want to count is actually 6 times 6 because we want to capture every single pair here. So here is going to be 6 over 36. So the answer is 1/6. Any questions? Here the denominator was a little bit trickier. All right, we'll do a couple more practice problems. All right, so this one's also about choosing 2 things now. So here, Johnny is dealt 2 cards from a standard deck of 52 playing cards. Find the probability that his 2 cards are of the same rank. So for example, he gets a pair of aces or a pair of 9s. And remember, for playing cards, we have 4 suits. There's hearts, diamonds, and then there's clubs, and there's spades. And then we have 13 different cards. So it's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we have jack, queen, king. So does anyone want to take a stab at how would we do this one?
I wanted to clarify something about the question.
Yeah.
Is like, let's say the ace of hearts and the ace of diamonds. So we have to, is different from the ace of hearts and the ace of clubs, right?
Yes.
So
Yes.
there'll be two different possibilities.
Mm-hmm.
Okay, thank you.
So I'm going to start by writing out sort of our formula for probabilities. So probability 2 cards are the same rank, number of ways Johnny gets a pair over number of total, let's say like 2 card sets. So now we can count sort of the top and the bottom. So how many ways can Johnny get a pair of cards where the pairs, 2 cards of the same rank? So 2 aces, 2 twos, 2 threes, 4s, etc.
Will it be 26?
Why is that?
No, because like, okay, so we can get 2 of hearts and 2 of diamonds, and then we can also get 2 of clubs and 2 of spades. So there are 2 different possibilities for the same number, and then there are 13 cards into, sorry, 14. That's 28 then.
So I guess there's different ways you can count it, but if you want to count the whole thing, basically there's 13 ranks, and then for each of those ranks there's 4 choose 2 ways to get 2 suits of it. So I can pick heart diamond or heart club or heart spade or diamond club, diamond spade, or club spade. That's 6. So this is 13 times 6. And then the number of total ways we can pick 2 cards is, here we're going to use combinations, 52 choose 2.
Why 4 choose 2?
So 4 choose 2 because we have 4 different suits, and we need to account for every pair. So let's call this H for heart, diamond, club, and spade. So we can have heart, diamond, heart, club, heart, spade, diamond, club, diamond, spade, or club, spade. And so there's 6. Or you can say there's 4 of them and we need to choose 2. So if we were to expand this out, this becomes 13 times 4 times 3 over 2 times 1 over 52 times 51 over 2 times 1. If we were to simplify this, basically we'll get, so the 2 and the 1s cancel. 13 times 4 cancels with 52. So we get 3 over 51, which is 1 over 17. So this is definitely like one way we can apply the formula, just kind of directly, and we'll get 1 over 17. I want to explain, before we move on, another way that we could solve this problem. So we can sort of transform this problem. Here it's saying Johnny Chan is dealt 2 cards from the standard deck of 52 playing cards. And so when we count the total number of ways, we are counting how many ways does Johnny get a pair over how many total pairs are there. But another way we could think about this is say Johnny is dealt something. First, Johnny is dealt 1 card, right? And that card could be anything. What's the probability that his second card has the same rank as the first card? Does everyone see why that is the same probability as what this is saying, what this problem is asking?
Yes, please.
Yeah. Let me just write it down for clarity. So we could transform this problem into Johnny is dealt a card. What is the probability his second card is the same rank? And if we try to calculate this probability, we kind of can use that formula, probability, second card. So basically we get probability 2 cards, same rank, equals the probability his second card is the same as the first card. And so in that case, we have the number of cards that match or that have the same rank as first card over the total number of cards that could be his second card. So if we count this directly, basically we know there's 51 cards left for Johnny to get after he's already been dealt 1 card. And then the number of cards that have the same rank as the first card, there's only 3 of them left in the deck. So we can count that as 3 over 51, and that just gives us 1 over 17.
Wait, but I have a problem with the first one. Since here you said he's dealt a card, so it will be left with 51. And the first one, since he's dealt 2 cards, wouldn't it be left with 50?
So basically in the you're talking about the second solution we're discussing?
The second one we just did, you said since he has dealt a card, you subtract 1 from the 52 to get 51. But in the first one, it says he has dealt 2 cards. So shouldn't we subtract 2 from 52 to get 50?
So if he's dealt 2 cards and there's 50 left, in this case, we're considering the case once Johnny has been dealt 1 card and we want to calculate the probability that the second card matches the first card. So when he's being dealt the second card, there's 51 choices for the second card.
Okay, I understand.
Yeah. So let's go back to this problem of 2 fair 6-sided dice. We can actually do a very similar approach here. So here we calculated the probability that they're the same by looking at the total number of pairs and then looking at the total number of outcomes. But another way we could have actually done this is we think about what is the probability that the second roll matches the first roll. So if we have the first roll as any number, then their second roll, there's a 1/6 probability that it will match the first roll. And the reason we can do this in both of these problems, and to kind of simplify the case, is because we see that the first roll or the first card that's being dealt doesn't have an effect on the probability. So basically, like it doesn't really matter what number gets rolled first in this problem. What we really care about is whether the second roll matches the first roll. Same with this problem about cards. It doesn't really matter what card Johnny was dealt first, but we care about what his second card was. And so even though both of these will get you the right answer if you like count the total number of, you know, sets of 2 or count the total number of pairs of rolls, but it is also very helpful if you can recognize when we can simplify the problems. This will really help with harder problems where it would be difficult to solve without thinking about it this way. So I want to give a couple of examples of that. Any questions?
I'm sorry, but the second question, the cards that have the same rank as the first card, how is it 3?
Oh, it could be any card. So it could also be like if you have a 2 of hearts and a 2 of diamonds, then those are the same rank. So basically it's saying the number is the same. So so say like Johnny, the first card Johnny was dealt is a 2 of clubs. Then out of all the decks and all the cards in the deck, there's 3 more cards that would match that, which is 2 of hearts, 2 of diamonds, 2 of spades.
Okay, I get it.
Yeah. All right. Okay, let's try a different one. This one's interesting because it uses some things that we learned in previous weeks. So this one says a number is randomly selected from the first 20 positive integers. What is the probability that it is divisible by 2, 3, or 4?
The numbers that are multiples of 4 are only multiples of 2. So you only need to find those that are multiples of 2 and 3.
Okay, cool. Yeah, that is correct. So it doesn't really matter that it says 2, 3, or 4, because if we're counting things that are divisible by 4, we're already counting them by counting the ones that are divisible by 2. That's right. So how can we count this?
Okay, you can list all the numbers and cancel out the ones that are divisible by 2 and 3. So you cancel all multiples of 2. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. And you can cancel all the ones for 3, which are 3, 6, 9, 12, 15, and 18.
Cool. So here we have probability select a number divisible by 2 or 3 or 4. You said that was the same as the selected number being divisible by 2 or 3. Basically, we want to count total number of numbers in, so 1, 2, all the way to 20, divisible by 2 or 3. And then here we just have number in 1, 2. Okay. And so the denominator is easy. That's just 20 because there's 20 numbers and we want to count the numerator. So what you were suggesting, Anna, was basically we can write out all the numbers and count how many are divisible by 2 or 3. So we could do that. Let me just use a different color. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we could say circle all the ones that are divisible by 2. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Then we can circle the ones that are divisible by 3. So that's 3, 6, 9, 12, 15, and 18. So then if we count how many are circled, that's 2, 4, 6, 2, 4, 6, 8, 10, 12, 13. Right, so then we can fill this in as 13 over 20. Is there another way we can count how many numbers in 1 to 20 are divisible by 2 or by 3?
We can just divide 20 by 2 and then divide it by 3, and that will give us the number of multiples available. And then we get rid of all multiples of 2 and 3 so that we don't overcome.
Yeah. So if you remember, I think 2 weeks ago we talked about principle of inclusion, exclusion. And basically the idea is if you have some set of numbers, let's say this is the set of numbers divisible by 2, and numbers divisible by 3, and then their intersection is numbers divisible by 2 and 3, which is by 6. Then basically we see that the number of numbers that are divisible by 2 or by 3, which is the union of these two sets, equals the number in here plus the number in here minus the number in here, because we're counting it twice. And to count each of these, we can basically kind of divide 20 by 2 by 3 by 6 and round down. So here we have 20, choose 2. This is the floor symbol, which kind of means you round down to the nearest integer. This is 20 divided by 3, and this is 20 divided by 6. So here we have 10 plus 20 divided by 3 is 6 point something. So we plus 6, and then 20 divided by 6 is 3 point something. So this gives us 13 as well. And the reason I want to highlight this is, you know, for 20, it's actually not that hard to write out all the solutions here, all the numbers 1 through 20, and kind of count. But if I change this problem to say, like, you know, I selected a number from the first 1,000 positive integers, then we want to count it using something like principle of inclusion exclusion, as opposed to writing out the first 1,000 integers. So here, 13 over 20. Any questions before we move on? All right. So for a bunch of these problems, we can kind of solve it just using like counting how many possibilities there are. Maybe we just like know that there's, you know, 6 ways to pick something, or we just kind of transform the problem and think, okay, the probability that the second roll matches the first roll is 1/6. But we also have a way to basically just finding the next. We also have other techniques that we can use to solve more complicated probability questions. So some of the counting methods that we can use could be combinations, which we learned about last week and the week before. So let's look at an example of some problems where we actually want to use combinations to basically help us solve it. So in this example, we see a fair coin is flipped 5 times. Find the probability that the coin lands heads up exactly 3 times. And so here, it's going to be hard to list out all the different ways that the coin could land 3 times. Of course, we could try. So we could say like, okay, coin is flipped 5 times. We could do like heads, 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 tails, tails, or heads, heads, tails, heads, tails, heads, heads, tails, tails, heads, etc. Right? But if we wanted to list out all of them, it would take a while. And we wouldn't be sure that we like necessarily got all of them or didn't duplicate. So it would be a lot more work. And so we could see that for the numerator here, the way that we could count this is basically saying how many ways can we order 3 heads and 2 tails. And this was something we learned about before, right? So does anyone remember how to do this?
Yeah, it would be 5 choose 2.
Yeah, so we could do 5 choose 2. Which is basically saying, okay, we have 5 flips and we need to choose 2 of them to be tails. Another way you could think about this is we have 5 flips, we want to choose 3 of them to be heads. And then sort of another way you can think about this is I have 5 flips and basically I have to order, 3 H's and 2 T's, and then I have to correct for overcounting. So there's 3 H's I have to correct for and 2 T's I have to correct for. So all of that will give you the same number, which is 10 in the numerator. Now for the denominator, we have 5 coin flips, and we want to see how many total possibilities there are for 5 coin flips. So I guess the answer is here, but basically for each coin flip, I can have 2 outcomes. It could be heads or it could be tails, and I do that 5 times. So for the denominator, we actually do 2 times 2 times 2 times 2 times 2, or 2 to the 5th, and this is 32. So the total here is going to be, sorry, it's hard to read. Basically this, 5 choose 3 on the top and 2 to the 5th on the bottom. So that gives us 10 over 32, which gives us the final answer of 5/16. So this is fundamentally the same formula as before. We want to count the number of successful outcomes over the number of total outcomes. But it's a little bit harder to count how many successful outcomes there are and how many total outcomes there are directly. So we're going to rely on the counting techniques that we learned previously to count them more effectively. Any questions about this example? All right. So then let's do a couple more examples together. So let me switch to this. All right, so we're back to marble selection. So here we say we have a bag that has 10 marbles. 6 are blue and 4 are green. 2 of the marbles are randomly selected from the bag without replacement. So what's the probability that both of them are blue? So I'll do an example first, and then we can do the other sub-problems together. So if we want to count how many are both blue, we can recall probability both are blue equals, so the number of ways we can select it, where we have 2 blue marbles, over the number of total selection of 2 marbles. And so if we have 10 marbles and we need to choose 2, then the total number of ways we can do that, let's say it's just 10 choose 2, or we could say there's, I guess there's different ways. I'll talk about this way first. So we can say 10 choose 2, we're picking 2. And then for the top, 6 of them are blue, so we're doing 6 choose 2, because we're picking 2 of the blue marbles. And then this gives us 30 over 90, which is 1/3. Another way you can think about it is, it doesn't really matter, but here we're saying, okay, well, the order doesn't matter, I'm just picking 2 marbles. You can also think about like, well, the order, let's say the order matters. We have like 1 marble, we'll call it marble A, that the first marble we pick.
Excuse me, wouldn't the previous one be 30 out of 45 rather? And not 90?
Yeah, well, I mean, okay, so we could do, here, let me. So technically, if I do 6 choose 2, there's a couple ways you could do it. So you could write it out 6 times 5 over 2 times 1 over 10 times 9 over 2 times 1. So this, if you calculate the numerator and the denominator, you would get this is 15 over 45, or you could sort of simplify this by getting rid of the 2 and the 1. Then that's how I got 30 over 90.
Okay, yeah, I get it, yeah.
Yeah, sorry, it's a bit unclear. Another way we could think about this is, say we just label the first marble we get, we put it aside as like marble 1, then the second one we put it aside as marble 2. We can also just count sort of permutations, 6 times 5 over 10 times 9. This would give us 30 over 90 as well, which is 1/3. And the key here is to make sure we're counting the top the same way as we're counting the bottom. Finally, another way we could do this is similar technique to what we did before. So basically we could say, all right, there's like basically there's one, or I guess it's a little bit different, but basically there's 6 out of 10 ways that, 6 ways that we would choose a blue marble first, and then 10 ways that we could choose a marble total. And then the probability that the second marble we choose would match that would be 5 over 9, because there's 5 marbles left that are blue and 9 marbles left that we're choosing. So this is also the same. I'll give you 30 over 90. So all of that is to say, we could count this in different ways, but the answer is going to always be the same. It's 1/3.
Could we use the pi for this?
Not for this problem in particular, because we just need to check that both of them are blue. I'll show one more way we could do this, and it's written out here, which is kind of helpful. So basically we could pretend that we label the marbles 1 through 10. So maybe we label the blue marbles like 1 through 6, and then the green marbles will label 7 to 10. And then we basically can count the total number of outcomes by, we could try to list out all the ways that we could select these 2 marbles. So for example, I'm looking at this chart here. We can first select marble 1, then marble 2, or marble 1, then marble 3, or 1, 4, 1, 5, all the way to, 10, 1, 10, 2, to 10, 9. And so if we write out this chart, that's another way to see that we have 10 times 9 total outcomes if we care about the order. And then out of these, how many ways are we selecting 2 blue marbles? So basically we could see there's 6 ways to select a blue marble on the first draw. That would be like, first we select 1, or 2, 3, or 3, And so all the way to like 6. And then once we select the first one, there's 5 ways to select a blue marble on the second draw. So then we have 6 times 5 total ways. So now let's do one together. Let's do part C. So find the probability that both of the marbles are green. And remember, we have 10 blue marbles. Sorry.
No,
We have
it's
6
10
blue
total marbles.
Yeah, 6 blue marbles. And then we had 4 green marbles. So what's the probability that both are green? Using the technique we just talked about.
4 choose 2 over 10 choose 2.
Yeah. So we could say if the order doesn't matter, we're doing 4 choose 2 over 10 choose 2. Or we can say, if we are counting the ordering, say we first select one, then we select the other, we can also just do directly 4 times 3 over 10 times 9. And then this gives us 12 over 90, which simplifies to 2 over 15. All right. So then let's do the middle one, which is a little trickier. So what's the probability that one is blue and the other is green? Any ideas?
There are 6 blue marbles and 4 green marbles, so we could multiply them together total and divide it over 10 choose 2.
Yeah. So basically there's 6 times 4 ways we can choose 1 blue and 1 green out of 10 choose 2 total ways. So this gives us 24 over 45, which is 8 over 15. Another way we could count this is we can first choose 1 blue marble, then 1 green marble, or we can first choose 1 green marble, then 1 blue marble, and then we could, choose 10 marbles first, and then 9 marbles out of 9 marbles second. And this again gives us the same one. It's just whether we count the ordering or not. So this gives us 48 over 90, which is the same as 24 over 45. So finally, let me zoom out a bit. We calculated 3 probabilities here. So we selected the probability found the probability that both are blue. We found the probability that one is blue and one is green. And we found the probability that both are green. And that covers all the different cases, right? There's no other way to select 2 marbles. Either they're both the same color and they're blue, they're both the same color and they're green, or they're different colors. And so an important property here is that the probabilities add up to 1. So let's check to see if that actually is the case, since we have covered sort of mutually exclusive and comprehensive cases. So for part A, we got that the answer was 1/3. For part B, we got that the answer was 8/15. And for part C, we got that it was 2 over 15. So what does that equal?
1.
15 over 15, which is 1.
Yep, this is 1. Does everyone see why it should add up to 1?
Yeah.
Cool. All right, so let's do more problems where we have to use counting techniques to calculate the probability. This one's a little bit trickier, but I thought it'd be fun to do it together. So this question says, James writes down 15 ones in a row, and then he randomly writes plus or minus between each pair of consecutive ones. So for example, here he wrote down 15 ones, and then he wrote down some pluses and some minuses between them, and then he wants to evaluate the value here. And so here the question says, what is the probability that the value of the expression that James wrote down is 7?
If
Any
the value is
ideas?
equal to 7, there must have been 8 negative ones and 7 positive ones. That way, when you add them, you get 7. So I'm not so sure, but I think the total way of doing this would be 15 to 7.
So that's close. So basically, I think you identified a key part of the problem, which is if the value of the expression is 7, then we need to identify how many pluses James wrote and how many minuses James wrote, right? And one thing to note is we have 15 ones, but if we write down plus or minus between each pair, James is writing down 14 total pluses and minuses. And the reason is because the first one has sort of this implicit plus in front of it, right? So he has 14 total. And we want to see how many are pluses and how many are minuses if the total value is 7. So there's a couple ways we can do this. We could kind of guess and check and say, okay, if there's like this many pluses and this many minuses, do we get 7? So in this example, we have, 1, 2, 3, 4, 5, 6 pluses, and then 1, 2, 3, 4, 5, 6, 7, 8 minuses, and then we sort of have this plus at the front. So in this example, it was 6 pluses, 8 minuses. And if we calculate the value of the expression here, we get 1 plus 1 is 2, plus 1 is 3, minus 1 is 2, minus 1 is 1, plus 1 is 2, minus 1 is 1, plus 1 is 2, and then we minus 1, minus 1, minus 1, that becomes minus 1, and then we plus 2, that becomes 1, then we minus 1, we get 0. Did I do that right? That's wrong. It should be minus 1. So this is 2, 3, 2, 1, 2, 1, 2, 1, 0, minus 1. Minus 2 plus 1 becomes minus 1, plus 1 becomes 0, minus 1 becomes minus 1. Yeah. So we could kind of slowly add this up, but actually a faster way to do this is, remember when we add things, we can actually like add and subtract, we can like rearrange the order, right? So if we have 6 pluses and 8 minuses, then really what we want, the thing we're calculating here is, and let's count this implicit one as a plus. So this actually is 7 pluses and 8 minuses. Then basically we have 7 positive ones plus 8 negative ones. So this is 7 minus 8, which is negative 1. So back to this thing about we want the value to be 7. We can kind of guess and check. as one way. If we guess and check, then basically we have two numbers, x minus y, and that equals 7. And then we also know that the two of them have to sum to 15 because there's 15 total numbers. Right. So if you guess and check, you can get an answer, but also we can solve the set of equations to get the answer. So there's different ways we can solve this. One way we can solve this is kind of isolating a variable. This is easy because we can say like, okay, we'll subtract the first, or we can add the equation to the other equation and get 2x equals 22, so x equals 11. Then we can plug it in to get 11 minus y equals 7, so y equals 4. Or you can kind of guess and check and say, okay, if I have two numbers that sum to 15 and the difference is 7, then maybe it's like, 8 and 7. Oh, that doesn't quite work. Maybe it's 9 and 6. Oh, that doesn't quite work. Maybe it's 11 and 4, and you get it. So then that means we need 11 positive ones and 4 negative ones. And then if we go back to these pluses and minuses, remember the first one is sort of always a positive one. And so that means James writes down 10 pluses and 4 minuses. Any questions on how we got to that?
So if the question instead of 1, it was 2, we subtract 2 from the 15.
What do you mean?
Like
mean-
in the question, they wrote 1 plus 1 plus 1 minus 1, etc. If it was 2 instead of 1, are we going to subtract 2 from 15?
So you mean if it was 2 plus 2 plus 2 minus 2, like basically you have a bunch of 2's and James is putting pluses and minuses between the 2's?
Yes, we subtract 2 from 15, like how you subtracted 1 from 15.
Oh, I think you would subtract 1. So the reason I subtracted 1 from 15 was because you have 15 numbers here, but you basically have only 14 things in between the 15 numbers to insert signs. So basically, if you think about how many pluses and minuses James is writing down, there's only 14 that he's writing down, because the first, you can think of it as like the sign that he's writing down gets sort of like paired with the number after it, right? Because if I say -1, that's sort of saying, okay, I'm subtracting the next number 1. And so there's 14 of these pairs. And then the first one is always this like +1. And so if the 1s were 2s, it would still be the same, because James would be still writing down 14 signs in between the 15 2s.
Okay.
All right, so now we've got that there's 10 pluses that he's writing down and 4 minuses. So we can go back to calculating the probability. So here, again, we want to count total, so probability that the value is 7. We want to count the total number of successes, which is total number of ways that James can write down pluses and minuses, such that it sums to 7 over the total number of ways he can write down pluses and minuses at all.
So is it possible that they could all be minuses or all be pluses?
Yeah, it's possible, but then it's not going to sum to 7. Or it's not going to evaluate to 7, right? So if I do all pluses, that's going to evaluate to 15. Or if I do all
Okay, but I'm talking about
minuses,
the total, the number of the total. Is it possible that in randomly putting them down, he could just write all minuses or all pluses?
Yes, it is possible.
Then in finding that, I wanted to say, ask if we could make it like the stars and bars, where there'll only be one bar and two sides. So if there's a star on this side, that star will be positive, and if there's nothing there, that star will be negative. So the number of ways to do that would be the number of ways to write the stars and the pluses and minuses.
I don't think this is a stars and bars question. Maybe let me explain how we would calculate it, and then we can talk about if you still think stars and bars would make sense here. But for the total number of ways, basically we see that James has to write down 14 signs in order, and for each of the signs he can write one of two possibilities. So he can write a plus or a minus. So the way that we would count that is basically do 2 to the power 14, because he needs to write down 14 things, and for each of those things he has two choices. So in this case, I feel like it's not really a stars and bars problem, because we're not it's not the same problem as trying to say like put 14 balls in 2 urns. And then when we look at the number of successes, it's also a different kind of problem. So number of successes, we basically want to see how many sequences are there of 14 signs, such that exactly 4 of them are minuses and the rest are positives or pluses. So for this, we actually could do 14, choose 4, because we can think of it as we have 14 signs that James has to fill in, and he has to pick 4 of them to be negative. And so if we want to simplify this, then we're going to get 14 times 13 times 12 times 11 over 4 times 3 times 2 times 1 over 2 to the 14, which is 14 times 13 times 12 times 11 over 4 times 3 times 2 times 1 times 2 to the 14. And then we can kind of simplify this. So for example, 4 and 3 cancel with 12, and then 2 cancels with 14, 7. So this gives us 7 times 13 times 11 over 2 to the 14, which is, I'm not gonna necessarily expand it out. Write it like this. So this one was trickier. Any questions? But it still has a fundamentally like same approach, right? We want to count the number of successes over the number of total ways. It's just a little bit trickier to count the number of successes. And then the other way, I think, to connect this to what we were doing in previous weeks is this is almost like two, like we could break this down into 2 subproblems. Each of the problems is very similar to a problem that we've solved in the past. So like the first problem is, you know, how many different ways can James write down 14 signs in order where each sign is positive or negative? And so that's a counting problem that we solved in the past. It's 2 to the 14. The second subproblem is how many ways are there for James to write down 14 signs where 10 of them are positive and 4 of them are negative? And that's also a counting problem we solved in the past. It's 14, choose 2. And then we have to put those 2 together to compute the probability. All right, any questions? If not, we'll do some more examples. All right, let's try this. 6 distinct integers are picked at random from 1, 2, 3, like the set 1 through 10. What is the probability that among those selected that the second smallest is 3? So any ideas on how we can do this? So let's do the denominator first. Usually that's a little bit easier. How many ways can I pick 6 integers?
10 choose 6.
Yeah. Cool. So now we have to deal with the numerator. So we want to see how many subsets of 1 through 10 has the property that the second smallest of them is 3. So if we had a set like that, it would have to look like, you know, some number A that's less than 3. Let's say I'm ordering these from least to greatest. Then 3 has to be in the set. And then I have, you know, maybe B, C, D, E. And so we can look at how many ways there are to choose these numbers. So for A, since it has to be less than 3, we can basically choose A from the set of 1, 2, right? So A could be 1 or A could be 2. So there's 2, choose 1, or 2 ways to choose A. How many ways are there to choose B, C, D, and E?
Would it be 7 choose 4?
Yeah, can you explain to everyone why that is?
Because 10 minus 3 is 7. That is all the numbers after 3 within the sets 1 through 10 are 7. And since you're only going to choose 4 of that, since you already have the first 2, it's going to be 7 choose 4.
Yeah, that's right. So basically, B, C, D, and E have to be in the set 4, 5, 6, 7, 8, 9, 10. And so there's 7 numbers total, and we want to choose 4 of them. So then the total number of ways that we can pick this set is 2 choose 1 times 7 choose 4. Does everyone see why that is? Where second smallest is 3. So if we put that together, then the total probability is actually 2 choose 1 times 7 choose 4 over 10 choose 6. And if we simplify this, we get 2 times 7, 6, 5, 3, 2 over 10, 9. I'm going to write this as 7 choose 3, write this as 10 choose 4, 10, 9, 8, 7 over 4, 3, 2, 1. And one thing I do to kind of calculate probabilities is usually I don't expand out the values until the very end, because if we keep it in sort of this like product, rewrite it as a product, then it makes it easier for us to simplify the fraction in the future. Because if you multiply it all out at the beginning, then you have to factor it again at the end to simplify the fraction. So usually I just do it all in one step. So here we can basically
Wendy,
say, yeah.
Since you made it 7 choose 3, wouldn't there be a 4 multiplying the 7 times 6 times 5?
So remember, these are the same. So 7 choose 4 is 7 times 7 factorial over 4 factorial times 7 minus 4 factorial, which is 7 factorial over 4 factorial, 3 factorial. So you could write this as 7 times 6 times 5 times 4 over 4 factorial, or you could write it as 7 times 6 times 5 over 3 factorial. So these are all the same expression.
Okay, yeah, thank you.
Yeah, okay. Cool. So let's simplify this. So basically I'll just like cancel stuff out. So the 6 cancels with the 3 and the 2. On the bottom here, the 2 and the 4 cancel with the 8. The 3 and the 9 cancel and give you a 3. And then the 7s also cancel here. And then the 2 and the 5 cancel with the 10 here. So this gives us 1/3. If I simplify that correctly. Any questions on this one? All right. I have some more practice problems. So just we can see a bunch of different types of these. So this one is a little different. So it's back to cards. So say you're dealt 5 cards from a standard 52 card deck. What is the probability that you get a full house, which is 3 of a kind and 2 of a kind? So let's start with the denominator again. So how many ways are there to choose 5 cards out of 52 cards to get the hand?
52, choose 5.
Right, so there's 52, choose 5. I won't expand it out for now. Ways to choose 5 card hand from 52 card deck. Cool. All right, so now we want to count the number of full houses. So any ideas on how we can do that?
Just for clarity, when they say 3 of a kind, does it mean 3 hearts, 3 diamonds, 3 club, or it means 3 ace, 3, or I'm not so conversant with cards, so forgive me.
That's okay. That's a good question. So in this question, since they gave the example of queen, 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 8, 8, it means that it's 3 of the same number. So it would be they could be different suits. So basically you want like 3 queens or 3 2s or 3 5s, and then 2 of another number or rank. So it could be like 3 5s and 2 kings, or 3 queens and 2 8s. So the suit doesn't
Ms.
matter
Wendy-
as much.
Yeah, Ms. Wendy, I was thinking since we could lay it out like they've written it there, QQ8, instead we just put dashes. And then since for it to be we have the 52 cards, we have to just pick one card, and we'll say we have this many left to choose from, but we know that afterwards we can only pick the same card. Or I was also thinking we could do 52 choose 3 or 52 choose 2 to get that.
Okay, yeah, that's close. There's a lot of properties we can use here, right? So I like your first idea, which is, we can think about, how can we form this hand, right? And so we can break this down into, we first need to pick, in this example, 3 cards that are the same rank. So the number of ways we can do that is we can choose 13. Out of the 13 ranks or values of the cards, we can choose one of them to be the 3 card one. And then for each of those ranks, there's 4 suits. So we can choose choose 3 of those 4 suits to be the 3 that we have. So for example, for queens, or for QQQ88, we have 13 choices for, you know, whether it's a ace, 2, 3, 4, 5, whatever, all the way to queen and king. And then out of the 4 suits, we can choose 3 of them to be the 3 that we pick out. So there's 4 ways we could do that. It could be like heart, spade, diamond, or heart, club, diamond, or heart, club, spade, or it could be spade, diamond, club. And then we can move on to, I'll use a different color, the second part, which is now we have to pick 2 other cards to complete the full house. And so since we've already selected one of the 13 ranks to be the 3 part in the full house, that means there's only 12 ways that we can choose one of the 12 ranks to be the second one to be represented in the full house. And then since there's only 2 of them, there's 4 choose 2 ways that we can select 2 suits for that number. And then we basically want to multiply this and this together. Any questions on that?
Yeah, please, I didn't get why we have to divide by 4, choose 2. The latter
So
part.
yeah, so basically there's, so say we've already picked 3, we've already chosen 3 cards to be the 3 of a kind in the full house. Now we want to see how many ways we can select the 2 of a kind in the full house. So we've already used up one of the numbers for the 3 of a kind. So say we picked queen, that means the last 2 cards, they can't be queen. So there's only 12 other possibilities. And then since we're picking 2 of them, there's 2 ways that we can pick the different suits. So remember there were 4 suits. There was heart, diamond, and then in the black suits there was spade, and there was a club. So if we want to pick 4 of them, we can, let me just label hearts, diamonds, spades, clubs. Basically there's 4 choose 2 ways to pick 2, or if we want to list them out, it'd be like hearts, diamonds, hearts, spades, heart, club, diamond, spades, diamonds, club, spades, club. And this is same as 4 choose 2. So basically for a given number, how many different pairs are there in the deck? And there's 6 of them. Does that answer your question?
Yes, thanks.
Okay. So then going back to the probability part, we've calculated sort of the numerator and the denominator. So the total probability that a random hand is a full house is equal to 13 choose 1 times 4 choose 3 times 12 choose 1 times 4 choose 2 over 52 choose 5. And we can simplify this together a bit. So the top becomes 13 times 4 times 12 times 6. And the bottom becomes 52 times 51, 50, 49, 48 over 5, 4, 3, 2, 1. And let me just invert this so it's a bit easier to reason about. 13, 4 times 12 times 6 times 5, 4, 3, 2, 1 over 52, 51, 50, 49, 48, right? And then we can simplify this So 13 times 4 is 52. What else can we do? We can do 5 times 2, here's 10. We can do 4 times 12 is 48. And then I think 3 goes into 51, 17 times. Did I do that right? I think so. So this becomes 6 over 17 times 5 times 49. And then if you multiply that out, I believe you will get 4165. Any questions on this problem? Cool. All right, so we did a lot of combinations here, and in the handout there's more exercises, so as homework I'll ask you to go through them. But we did a fair number of them together. So next I want to talk about probability with casework. So basically remember, casework was another technique that we learned about how to solve counting problems. So sometimes when things are complicated, we might have to break the counting problem into multiple cases. Similarly, when it comes to probability, we might also have to do the same thing to count either probabilities by cases or the numerator in different cases or the denominator in different cases. So let's take a look at some examples on how to basically combine casework with what we learned about probability. And again, this handout has a lot of questions, but we'll go through just some of them together. So here's an example. Harold tosses a nickel 4 times. Determine the probability that he gets at least as many heads as tails. So any ideas on how we can do this problem?
Well,
Okay,
we
so
start using the 3, and it would go for the first round. He can choose either heads. He can land either heads or tails. That's split down into head after heads or tails, and heads and tails. He lands on tails, and so on and so forth. So we reach the 4th attempt.
Yeah, so let's break this down into, again, like the 2 things we want to count. So first, let's count, so we want probability at least, or let's just say probability the number of heads is greater than or equal to the number of tails. All right, so that's what it means to be at least as many heads as tails. And then let's write it down as the fraction of successful outcomes over total outcomes. So here we have probability number of ways to flip it such that number of heads is greater than or equal to number of tails over number of sort of ways we can flip 4 nickels. So how can we count the top and the bottom? So let's start with the bottom. I think that one's a little bit easier. Any volunteers on how many ways can Harold toss 4
That would be
nickels?
2 raised to the power 4.
Yeah. All right, now what about the numerator? Count the number of ways that Harold can toss a nickel 4 times, such that there's at least as many heads as tails. And there's a hint here, which is we could use casework for this. So what are the cases?
When heads equals tails, so there's 2 heads and 2 tails. When there's 3 heads and 1 tail, I think, yeah.
Right, so it could be 2 heads, 2 tails. It could be 3 heads, 1 tail. Finally, it could be 4 heads, 0 tails. So here are 3 cases. And then for each of these cases, let's count how many ways Harold can toss the nickel to get that outcome. We can start with the easiest one, which is if there's 4 heads, then there's only one way that Harold can do that. It has to be heads, 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 right? So there's 1 here. What about case 2? How many ways can Harold toss a nickel 4 times to get 3 heads and 1 tail?
That would be 4 choose 1.
Yeah, choose 4, choose 1. And then what about case 1? 2
4
heads and 2
choose
tails.
2, 6.
Yeah, 4 choose 2. So this is 6. So then to get the total number of ways, Harold can toss the nickel to get at least as many heads as tails. We want to add all of them. So this gives us 6 plus 4 plus 1 equals 11. So let's go back here. Put 11 here. So this gives us 11 over 16. Any questions?
I have a question. Not that it has to do with this, but usually they ask a question and say, represent your answer in a ratio in the lowest term. Would you leave it in an actual ratio as in this is to this, or you can make a common fraction?
Yeah, so when it says ratio, it's the same as a fraction. So basically what they're asking for is something of the form like 11 over 16 and not a decimal, right? So you don't want to write like 11 over 16 is 0.6875. So you want to write 11 over 16, not this. And then usually when they say simplified, it means you have to take out all the common factors. So for example, you don't want to write something like 22 over 32.
Okay, yeah.
Yeah.
Thank you.
Yeah, good question. We actually see that a lot when it comes to like probability questions, because oftentimes the problems will say just express it as a fraction. And so that's actually good for you too, because you don't have to do the long division to see what the decimal is. You can just leave it like 11 over 16. All right, let's try another one. It's a different type of probability problem, but again, here's one where Casework can help us. So this one says container 1 holds 8 red balls and 4 green balls. Containers 2 and 3 each hold 2 red balls and 4 green balls. A container is selected at random, and then a ball is randomly selected from that container. What is the probability that the ball selected as green? And then here we see express your answer as a common fraction. So what are the cases for this problem?
I think we should put them into containers.
Can you explain?
So you could make it container 1 as the first case, container 2 as the second, and container 3 as the third.
Okay. So case 1 is we picked container 1. Case 2 is we pick container 2. Case 3 is we pick container 3. Is that what you mean? Okay. So say we pick container 1. What's the probability that we draw a green ball when we draw from container 1?
Well, I was thinking we can do something like we sum and then we say 12 choose 4. What's the chance of choosing well, not choose 4, so maybe 4 choose 1 to see the chance of them choosing a green ball out of those 4 green balls. And maybe we then multiply it by the chance of them removing a green ball from that container. So 12 choose 4.
So that's close. So basically
I thought-
here we have two things that make up this this probability. So let's first think, okay, suppose we had already picked container 1. What's the probability that we, given that we've chosen container 1, that we pick a green ball? And so here we have 8 red balls and 4 green balls. So the probability that we select a green ball is just 4 over 8 plus 4, which is 4 over 12, which is 1/3. Does everyone see where that is?
Yes.
Yeah.
Okay. So 1/3 is the probability that I pick a green ball, given that I've already picked container 1. However, there's sort of this first step, which is first we select a container at random. So what's the probability that I pick container 1 in the first place?
1 over 3.
1/3, right? So now we want to calculate the probability. So let me write this out. Probability that we pick container 1 and select a green ball. So first, it's the probability we pick container 1 times
1 out of 3.
probability select. And before I write this out, this is an important concept, which is that you can multiply probabilities together when they're independent. And so I say independent because the probability that I pick container 1 is kind of, it doesn't have any bearing later on whether I select a green ball or not. It's like I pick the container and then I select the green ball. So if I want to calculate the probability that I pick the container and select the green ball, then I can multiply the two together. So in this case, we could do 1/3 times 1/3, which is 1/9. All right, let's do case 2. It's very similar. Any ideas on this one?
So this one to be 2 over 2 plus 4.
Actually, wouldn't it rather be 4 out of 2 plus 4?
So it's 1/3 that we pick container 2. And then there's 4 green balls and 2 red balls. So there's 4 over 2 plus 4. So this gives us 1/3 times 2/3, which is 2/9. And then what about case 3?
It will be the same as case 2, so 2/9.
Yeah, so case 3 is same as case 2. All right, so now we want to combine these together. So it says, what's the probability that the ball selected is green? And we have 3 cases that we've picked, which is if we pick, there's sort of this 1/9 probability that we pick container 1 and select a green ball. There's a 2/9 probability that we pick container 2 and select a green ball. And there's a 2/9 probability that we pick container 3 and select a green ball. So what's the probability that overall we'll select a green ball? How do we combine that?
We added the 3, giving
Yeah.
us 5/9.
Yeah, so in this case, we want to add them because we want to compute the probability that we select, basically the probability we pick container 1 or pick container 1 and select a green ball, or pick container 2 and select a green ball. or pick container 3 and select your green ball. So in this case, because we're sort of counting distinct cases and we want to compute the sum, we want to compute the probability that any of those cases happen, and also those cases are independent. We want to sum the probabilities. So here we want to do 1/9 plus 2/9 plus 2/9, which is 5/9. Any questions?
No, please.
So I just want to summarize like some things that we did here, right? So we have these kind of independent events. And so it's independent because what happens in the first event doesn't affect the probability of the second event occurring. So for example, if I pick container 1, container 1 does have like different balls, but once I pick container 1, it doesn't really affect like me choosing balls after I've already picked it. And so there's a couple of rules here that are useful. So if we want to calculate the probability that 2 events occur at the same time, this is very similar to our counting multiplication rule. So if we want to count the number of ways that 2 events happen at the same time, then we multiply. Same for probabilities. If we want to calculate the probability that 2 events happen and they're independent, then we can multiply them. The other thing that we used here was that if we want to calculate the probability that if there's 2 events that are independent and we want to calculate the probability that either of them happens, then we want to add it. So in this case, we could pick container 1 and select your green ball, or we could pick container 2 and select your green ball, or you could pick container 3 and select your green ball. And all of those events are like you can't have both of them happen at the same time. So when we want to compute the probability that any of them happen, we can actually sum the probabilities. And that's the same principle that we use for counting, which is like if we want to count the number of ways some things happen, then and those things are independent and you can't have them happen at the same time, then the total number of ways for them to happen is the sum of those ways. And so we'll use that a lot in probability, and especially in casework, we'll do a lot of summing. So let's look at another example for illustration. This one's a little bit more kind of algebraic with a little bit of number theory. So this one says, let A, B, and C be 3 not necessarily different numbers chosen randomly and with replacement from the set 1, 2, 3, 4, 5. Find the probability that A, B plus C is even. So it's a little bit trickier, right? Let's first think about, what are the different ways in which A, B plus C is even? Like, how do we even get this expression to be even?
Well, first we can look at ways in which we can produce even numbers. So if we take the multiplication, even number and an even number gives an even value. And if we get that even value, we add another even value to it. And then we have the multiplication being producing an odd number. And if it produces an odd number, then we have to add another odd number to it to produce an even value. And then we just go on, and then those could be our different cases. And then we'd experiment using the numbers we were given.
Yeah, awesome. So we could see basically what you're saying by, say we write out a chart of what happens, right? So if A is even, and B is even, and C is even, then AB plus C is also even, right? Let's say A is even. I'm just going to use even, E and O for even and odd, so I don't have to write as much. Say A is even, B is even, and C is odd, then A, B plus C is odd, right? So you have an even plus an odd. What if A is even, B is odd, and C is even? What do we get?
The results will be even.
Yeah. What about A is even, B is odd, and C is odd?
The results
The
will be
results
odd.
will be odd.
All right. Let's see, what cases haven't I gotten yet? Now, say A is odd. So I've gotten every case where A is even. Now say A is odd, B is even, and C is even.
The results will be even.
Even.
Yep. What about even, sorry, odd, even, odd?
The
Odd.
results will be
Yeah. What about odd, even?
Odd.
Odd.
And then odd.
Odd. Hey, sorry, even.
Yeah. Did I get all the cases?
I think you missed one even for A.
Which one did I miss?
No, I don't think you missed any.
I think I got all of them.
Yeah, you missed
One
even,
quick way you
even.
can, oh, that's the first one.
Okay. Then that's it.
Yeah, I think one quick way you guys could check, for example, is you can think about, okay, there's like 3 variables. Each of them could be even or odd. How many total ways are there? There's 2 to the 3, which is 8. And then we can count. We have, 8 cases here. As long as these 8 cases are all different. All right, so going back to the original suggestion, we basically can outline out all the cases where A, B plus C is even. And so we found there's 4 cases, right? A, B plus C could be even if A, B, C are all even, or it could be even if A is even, B is odd, and C is even, or it could be even if A is odd, B is even, C is even, or A, B plus C is even if all of them are odd. And so that could be our 4 cases. So let's write that down. Case 1, A is even, B is even, and C is even. Case 2, A is even, B is odd, C is even. Case 3, A is odd, B is even, C is even. In case 4, sorry, not enough room. Case 4, A is odd, B is odd, and C is odd. All right. So now let's find the probability that each of these cases happen. So in the first case, what is the probability that we pick A, B, and C from the set 1, 2, 3, 4, 5, where A is even, B is even, and C is even? Any ideas?
Well, we could say that since there are 2 even numbers, we can say 2 out of 5 would give us even numbers.
Okay, so that's a probability that we pick one number and that's even. But here we want to pick 3 numbers and they're all even. So is there any changes that we want to make?
Wouldn't that be 2 out of 5 all cubed?
Yeah, so 2 out of 5 is the probability that, say, we pick A and A is even. But now we also need to ensure B is even and C is even. So there's also a probability that I want to multiply here. And to kind of be more explicit here, since these are independent events, we can say this to the probability of A is even times the probability that B is even times the probability that C is even, which equals that. And if we write that out, that gives us 8 over 125. What about case 2?
That's 2 over 5 times 3 over 5 times 2 over 5. So 12 over 125.
Right, so again here, the probability that A is even, B is odd, and C is even, this is sort of and, equals the probability that A is even times the probability that B is odd times the probability that C is even, which is 2 to the 5th times 3 to the 5th times 2 to the 5th, which was 12 over 125. Cool. What about case 3?
It would be the same as case 2 because we're still doing with 1 even, 1 odd, and 2 evens.
Right, so it's the same. This is 3/5 probability that A is odd, 2/5 probability that B is even, and 2/5 probability that C is even. And then lastly, case 4.
That's going to be 3 out of 5 cubed, all cubed.
Right. So same principle here. Equals 3 to the 5th times 3 to the 5th times 3 to the 5th equals 27 over 125. All right, so now we want to compute the probability that A plus B plus C is even. So how do we combine all of this?
We
can
add them.
Yeah, so here we want to add them, right? Because probability A plus B plus C is even equals probability A even, B even, C even, or A even, B odd. Sorry, let's do or A odd, B even, C even, or A odd, B odd, C odd. So this equals probability A even, B even, C even, plus probability A even, B odd, C even, plus probability A odd, B even, C even, plus probability A odd, B odd, C odd. And that was what we just computed above, right? So as you all said, we want to add this up. So this equals 8 over 125 plus 12 over 125 plus 12 over 125 plus 27 over 125. And then if we sum this all together, this gives us 8 plus 12 is 20, plus 12 is 32, plus 27 is 59 over 125. Any questions?
No, please.
Awesome. All right. I kind of want to do, okay, let's do this one. I think it's a good question. So let's do one more in our last 5 or so minutes. This one's a little bit of algebra since I know you all learned some algebra last week. So here we see the question, coefficients A, B, and C of this equation, ax squared plus bx plus c equals 0, selected without replacement from basically the set n equals -4, -3, -2, -1, 1, 2, 3, and 4. And it says compute the probability that x equals 1 is a solution of the equation. So any ideas on how we could do this?
We can use the constant c and make it our case. We can have the case that we are either subtracting a certain value to make it 0, or we're adding a certain value to make it 0.
Yeah, so let's use this fact, right, that x plus 1 is a solution of the equation. So if we know x equals 1, if we know that when x equals 1, that's a solution, what does that tell us about a, b, and c together?
That it's basically a plus b plus c equals 0.
Yeah, so if x equals 1 is a solution, that means that a times 1 plus b times 1 plus c equals 0, which is a plus b plus c equals 0. So now we've changed this problem to say, okay, how many ways can I select a, b, and c without replacement from the set n such that a plus b plus c equals 0? And so we can use Casework to count this. So how many ways can I pick a, b, and c here?
So, like I was thinking, we could use the constants because the sum of the first two numbers might be canceled out by the constant c to provide 0. So if we put 2 and 1 there, we know we're putting -3 as our c to get 0.
Yeah, so basically you're saying a plus b, you can rearrange it to say a plus b equals -c. Is that what you're saying?
Yeah, either negative or positive c.
Yeah, I mean, that's the same. So yeah, you could say a plus b plus c equals 0, or you could say a plus b equals -c. Yeah, so basically, like, we could break it down into a couple of cases. So one case could be, let's consider the case where one of the numbers is positive. And then we could consider the case, let's call this case 1. And then we can also consider case 2, where two of the numbers are positive. And then we could also think about, like, is it possible for none of the numbers to be positive? And I would say no, that's not possible, because a plus b plus c equals 0. Or if you think about it as a plus b plus c equals -c, a plus b equals -c, you'll see that we can't have all the numbers be positive, because, or we can't have none of the numbers be positive. And then we also can't have all the numbers be positive. So we need to have some positive, some negative for it to add up to 0. And so now we can just kind of do some casework here. If one of the numbers is positive, what are some combinations that we can have for it?
We could do 4 choose 8, because there's 8 values and we're choosing 4 of the negative ones.
Oh yeah, but how do we make sure that this is true? A plus b plus c equals 0. How many ways are there to pick it such that their sum is 0?
You can pick any 3 numbers which from the set, which when you add them, you get 0.
Okay, so how many ways are there to do that?
Well, if we had 4 as our c, then, and 2 of them are, if we had -2 as our c and 2 of them are positive.
Okay, so let's consider what number could be positive, right? If one of the numbers is positive and it's 1, is that a possibility?
No.
Right, it's not, because we can't find 2 negative numbers that sum to 1 in the set n, right? What about if one of the numbers is 2? The positive number is 2. Can we find 2 negative numbers there?
No.
No. Okay, what about 3?
Yes.
Yes.
Yeah, cool. So we can do 3, and then what numbers would those be?
Negative
-1
2.
and
Negative 1 and negative 2.
Okay, cool. That's one set. And then what about 4?
-2 and minus and
Negative
sorry, -1
2 and
-3.
negative 1.
Yeah, -1, -3. Okay, so we have found 2 sort of possibilities if one of the numbers is positive. What about case 2? 2 of the numbers are positive. What sort of things
Well,
could we select for A, B, and C?
we can have 1 and 2 and then -3 and 1 and 3 and -4.
Awesome. Okay. So now we want to put this together, compute the probability. So here we found that there's 2 ways that we can kind of select a set of numbers such that they sum to 0. And if one is positive, and then we found there's 2 ways that we can select it if 2 are positive. How many ways are there for me to select 3 numbers from n total?
And choose 3.
Yeah, that's right. So the probability that all of them are 0, the denominator is going to be, so there's 8 numbers in the set n. So this is going to be 8, choose 3. And then we found that there's 4 total solutions that give us A plus B plus C equals 0. So if we expand this out, this gives us 4 over 8 times 7 times 6 over 3 times 2, which gives us 4 over 56, which is 1 over 14. So this one's a bit tricky. It required a lot of different steps. First, we had to think about, understanding what it means for x to be a solution or a root of the equation, plugging it in, and then we transformed it into a different problem. So instead of thinking about like A, B, and C as coefficients, we just wanted to see how many sets of sort of distinct A, B, and C exist such that they sum to 0. And then we calculated that probability directly. And then the casework we had is we just had a more organized way of counting how many different combinations from n exist such that the sum is 0. And we just divided it into 2 cases so it's easier for us to reason about. And then in order to count, we can just kind of check all of them. Because if one of the numbers is positive, then there's only like 4 things we need to check. If 2 of the numbers are positive, there's also only 4 things we need to check. And then once we counted that, we could say 4 is in the numerator, and then 8 choose 3 is in the denominator. Any questions on this one?
No, please.
Yep.
All right.
For
Oh,
the
yeah.
for the case 1, if one of the numbers is positive, could we rotate it and say it's also one case?
Can you clarify the question? I'm not sure I understand.
Let's say if you bought -1 first, could we swap it, like instead of 4 first, we bring -1 first?
Yeah. So this is another way you could solve it. So in this case, I'm sort of saying the order doesn't matter. But let me use a different color. You could say, okay, let's count the number of ordered triples, A, B, and C. In that case, in case 1, 4, 3, -1, -2, there's actually 3 factorial or 6 ways that you could have ordered triples. You could have like 3, -1, -2, or 3, -2, -1, -1, 3, -2, -1, -2, 3. I'll write out the other 2. Right, is this your question?
Yes.
And then for the other one, 4, -1, -3, there's also 6 cases. In case 2, we basically have the same thing. For 1, 2, -3, there are 6 ordered triples. And then same for 1, 3, -4, there's 6 ordered triples. So if we compute the probability this way, then P, A plus B plus C equals 0. We actually have 6 plus 6 plus 6 plus 6 in the top. But then at the bottom, we also need to take into account the fact that the order matters. So if we're picking 3 numbers and we care about which one is A, which one is B, which one is C, then the denominator is going to be 8 times 7 times 6. And so this will give us the same number. So this is 24 over 8 times 7 times 6, which gives us 24 over 56 times 6, which gives us 4 over 56. So it's basically like you can count the probability in different ways. But yeah, you could count it where the order matters and you'll get the same answer.
Okay, thanks.
Yeah, great question.
Wendy, please, can I have a look at the question?
Yeah. I'll send out these notes afterwards too. So you all can refer to it.
But it's kind of funny because the question is coefficients A, B, and C of ax squared plus bx plus c equals 0 are selected without replacement from the set N. Compute the okay, it's okay. I see my mistake. It's okay. My bad.
Oh, okay. All right. Well, thanks everyone for coming. I know I'm a little bit over time. I'll share these notes on Piazza. Please feel free to review it. For the homework, there's basically some extra exercises in the handout, and I would love for you all to go through everything up to the casework ones, and there's also solutions in there. And then if you have any additional questions about the homework or about any of the questions we covered today, feel free to just post on Piazza. All right, thanks everyone for coming.
Thank you. Bye.
Bye.
Thank you, Wendy.
Okay,
Bye.
thank you. Bye.
Thank you.